So I'm Vanderbauwhede from University of Glasgow, and I'm going to talk about the work that we propose to do to improve hardware security. So I say propose to do because this is a project that was started in end of February. So these are the partners: Glasgow, Heriot-Watt, another Scottish University, and Imperial College London. And we have VDF, ABB, and Xilinx as industrial partners. So I think the previous talk has much more in detail highlighted all the issues that we could have possibly with IoT devices and so on. So I'm not going to dwell on that for very long. Our focus is on systems on chip, and we want to make the design of systems on chip more reliable, let's say. So more, we want to give the designer a much greater control over the verifiability of the functionality through using advanced type systems. And so most of the talk will introduce what that means. So type systems are programming language features that help us to reason about programs, check programs' properties and things like that. And so in this work has the intention is really to use an advanced type system as a kind of contract that describes your design, and then you cannot implement it without you cannot violate the contract while implementing it, or otherwise your implementation cannot happen. That's kind of the idea. So we call the project Border Patrol, and that's a bit whimsical, I suppose, in retrospect, considering how times were nicer when we were designing this proposal. But essentially it means that we patrol the units of modules in a design. That's what it means. So basically, if you have an IP core in a system on chip design, you don't really know what's in the black box. You have an interface specification. If your interface specification is sufficiently formal, then you can actually create a circuit that will control the interaction between the black box and the rest of the system by patrolling the border, meaning checking all the signals that go in and out of this box. And that's kind of the idea. And by using a variety of techniques, we can do things like check the protocols that go over the connections in the chip, and check the value ranges, and even check derivatives and integrals and so on. So that's what we intend to do. So the reason why we want to do this is, well, if you've written any hardware in Verilog or VHDL, then you know that actually it's very hard to make this formal in any way, to verify that the system exactly does what the specification says, because the specification is not very tightly connected with the actual implementation code. And this is exactly what we intend to change. So we want to make the specification such that if you design in-house and your design does not match the specification, it won't synthesize. If you take a third-party specification, a third-party IP core, and it comes with its specification, but actually it's lying about its own specification, you will catch that at runtime. So that's kind of the idea. So we use a variety of type systems, and essentially, I'm not going to explain all the syntax. I'll try to give you an intuition of what all these things do and mean. But we use session types, dependent types, hybrid types. And what all these things are essentially ways of reasoning about the structure of your program instead of reasoning about the actual implementation of, say, functions in your program. So a dependent type is a type where you can reason about values. For instance, a very simple thing is if you have a type that says this is an array of integers, if you can say this is an array of integers of size n, well, then actually this n could be your dependence, because your runtime value has to be the same as that n. So that would be a simple example of a dependent type. In practice, if you use a language like Idris, which we use here, then these dependencies can be a lot more complicated than that. And they allow us to do things like checking against the ranges and checking against derivatives and so on. And that's the technology we want to use if we want to see whether values that pass over a bus are actually within the ranges that the designers desired them to be. So with this kind of types, you can essentially very much tighten the kind of code that you can write. So it becomes, in a way, much more restrictive because the type signature, which is this line at the bottom here, which in this case says that you have a vector, an array of size m and an array of size n. If you combine them, then the result must be m plus n. Now, that may seem obvious, but in many languages, you could combine them and violate that constraint, and it would still work. Right? So this is the kind of ability that we have. So another type system that we want to use heavily is called session types. And session types, the easiest way to think of them are actually formalizations of protocols. So it's a formal mechanism to express protocols. For instance, TCP. You could write out the whole TCP protocol as a session type description. And when you've done that, you can prove properties, and you can actually, for every participant in the system, validate its side of the conversation, let's say, and make sure it's correct. And again, this can be done either at design time, where you actually want to see whether the code you've written is correct, or you can use the specification at runtime to check whether what's happening is still according to the spec. So if you combine these things, then you get a very powerful mechanism for, let's say, validating that your system on chip design does the right thing. So this is just an example of a TCP IP handshake implemented in Idris. So essentially, let me see. Did I get? Oh yeah, okay. So this code here is actually the session type that describes the handshake. So this is not the code that executes anything. That's your specification. And then if you actually implement it, then you see that the type description at the top there has network handshake. So it's basically saying this is a network protocol that must obey this handshake type. And then if you write that code that actually does the handshake, which is very similar the way you would write it in any language except for the weird syntax, if it is not exactly following this handshake type, it will simply not work. So that's the idea. And then we want to use something similar, not to do TCP IP handshakes, but to do protocols in systems on chip. But actually, the concept applies. Now you can say, yeah, but if you have your black boxes, right, you don't know anything about them. The nice thing about session types is that actually there is a one-on-one correlation with finite state machines, which means that actually you can synthesize a finite state machine from the session type that you can use to check your protocol at runtime. So if you wrap your black box into a wrapper that has this checking state machine, then whenever this black box tries to do something that doesn't follow your protocol, then you can stop it from doing that. So that's the main mechanism that we intend to use to keep, let's say, untrusted components from doing any harm to the system. So, however, once we are on a roll like this, we can actually do more. So there is another concept called subtyping. And so if you've written any system on chip hardware and you didn't have a very nice IDE to help you, and you have two different standards, then you have to write glue logic to make them work. You have two bus standards, and okay, that's great. Glue logic, you're very careful, you're a good designer, and you manage. But it would be nicer if you didn't have to, right? So if you use a concept of subtyping, then essentially what it means is that you have a way to say that types are similar in a certain way, and if these types represent your protocols because they are dependent session types, then it's possible to actually either prove that they are compatible, or if they are not, you can actually provide a proof to say what should happen that they are compatible, and then you formalize your glue logic. And the difference is, well, it's formal, it's a proof, you can actually prove that it's correct. If you can then synthesize your glue logic from that, then your chances of getting it right are much higher. So that's kind of, in short, all the machinery that we intend to use to make hardware design much more reliable, let's say. So in practice, it means we need to create some kind of language that you can use as a system architect. For instance, if you would be using Xilinx SD SOC or something, that has a familiar syntax that lets you express your specification, but that actually ends up being compiled into our type descriptions so that we can do all this fancy type checking. Then we can all check all our own cores at design time, and we don't have to generate any actually border patrol modules for them. And all the stuff that we don't trust, we do synthesize extra stuff to the runtime check it. And so the interesting thing is actually, once you say that you have a system that can check protocols and can check values, then this actually applies to software as well, because what you can do is you can start checking whether your software is not exceeding the memory ranges that you have allocated for it, so that it's not trying to tamper with somebody else's memory space. Because you put your checking unit on the bus and you check those calls, right? And so if your software pretends or purports to follow some specification, you can see that it does actually follow it or not. So that way we can actually use it with real embedded systems that don't have just hardware but also software, because there are very few systems on chip that do not have a processor these days. So by doing all that, we really hope to increase safety and security of smart devices and help safeguard critical infrastructure. I mean, that's how it all started. That's why EDF is a partner. They were kind of worried about their next generation of nuclear power plants, something like that. And so we hope that this will be of benefit not only to the people that we keep safe, but also to the academic community as giving a new approach for designing systems on chip. And so I think that's actually already the end of my story. So thank you very much.